Hi, so today we're going to discuss black body radiation and Planck's theory, the photoelectric effect, the Compton effect, atomic spectra, and Bohr's quantum model of the atom and Bohr's correspondence principle. So we will now discuss black body radiation and Planck's theory. So we will see that light has particle-like behavior as well as the wave-like behavior we have studied previously in the light videos. And later we will also see that not only light but material particles have this particle-wave dual nature. So in the videos of thermodynamics, we have seen how an object at any temperature emits energy in the form of thermal radiation, and this radiation depends on the temperature and properties of the surface of the object. And at room temperature, the thermal radiation is primarily in the infrared region, which is invisible to the human. But as the temperature of the surface increases, the object turns red. Then at higher temperatures, it turns white, like for example in the case of the light emitted from a hot tungsten filament in a light bulb. So experimental studies on this radiation show that it consists of a continuous distribution of wavelengths, okay? And according to classical physics, thermal radiation is due to accelerated charged particles near the surface of the object. These charged particles can have a continuous distribution of accelerations, which accounts for the continuous distribution of wavelengths emitted by the object. But this classical model was not able to predict the shape of the curve of the intensity versus wavelength of a black body radiation. This is the curve here. Okay, so a black body is defined as an object that absorbs all radiation incident upon it. So a good approximation of the black body is a hollow object like this one with a small hole here or opening. So the radiation emitted from this hole depends only on the temperature of the cavity walls. Okay, experiments have shown that the wavelength distribution of the radiation from a black body at different temperatures is shown here in this figure, and it shows that the distribution of the radiated energy varies with temperature and also with wavelength. Okay. So 2 points were noted from the experiments. The first point is that the total power of the emitted radiation increases with temperature. As you can see, the total power is increasing with temperature, okay? And according to Stephen's law that we discussed in the videos of thermodynamics, the power emitted from a surface of area A and temperature T is given by this equation. And for a black body, the emissivity E is equal to 1, okay? And the second point noted from experiment is that the peak of the wavelength distribution, as you can see here, the peak is shifting towards shorter wavelengths as the temperature increases, okay? And this shift was found experimentally to obey a relationship known as Wien's displacement law. This is the law here. So lambda max is the wavelength at which the curve has its peak, and T is the absolute temperature of the surface emitting the radiation, okay? But as we have said, this classical model was not successful in explaining this dependence of power on temperature described by Stephen's law, or the shift of the peak with temperature, which is described by Wien's displacement law. And one of the early classical model attempts to describe this distribution of energy from a black body is the Rayleigh-Jeans law. So let's define here I lambda T d lambda to be the intensity, which is the power per unit area that is emitted in the wavelength interval of d lambda, okay? And here I will not include the details of the calculation, but it is based on the classical theory that the accelerated charges or oscillators in the cavity walls have a continuous distribution of possible energies and therefore emit electromagnetic waves at all wavelengths, okay? And this turned out later to be false. So as we said before, the black body is modeled as a cavity with a hole, and the inside walls of the cavity are perfect reflectors, okay, and the radiation inside the cavity is considered as a series of standing electromagnetic waves. Then using the theorem of equipartition of energy from classical physics, which we discussed in the videos of thermodynamics, the average energy per degree of freedom of an entity in thermal equilibrium at a temperature T is equal to half kT, where K is Boltzmann constant, okay? And note here in this case that each standing wave in the cavity originates from an oscillating electric charge in the cavity wall. So the classical average energy per standing wave is given by this equation because 2 degrees of freedom are associated with the wave. Okay, so this is the classical average energy per standing wave. So based on this, the Rayleigh-Jeans law is given by this equation, where Kb is the Boltzmann constant, okay? I'm plotting this theory as shown here with the experimental results of the black body radiation. You can see the discrepancy. And also from the equation itself, you can see that as the wavelength approaches zero, the function I approaches infinity. But as you can see here, the Rayleigh-Jeans law is in reasonable agreement with experiment at long wavelengths, right? So the experimental data of the black body does not show that the energy emitted by any black body becomes infinite when the wavelength approaches zero. Instead, as you can see here, it shows that as lambda approaches zero, the intensity also approaches zero. And this discrepancy was called the ultraviolet catastrophe. So in the 1900s, Max Planck developed a model that gives an equation for the wavelength distribution that is in complete agreement with experiment. And his model was the beginning of the field of quantum physics, okay? So in his model, Planck considered the black body radiation to arise from oscillators, and these oscillators include oscillating charged particles within the molecules of the black body, okay? And also he considered the oscillators emitting the black body radiation to be located at the surface of the black body. And in addition, one of the key points is that he considered the energy of the oscillator to be quantized, okay? Which means it can have only certain discrete amounts of energy En given by En equal to nhf, where n is the quantum number. And n is a positive integer, okay? And f is the frequency of the oscillator, and h is Planck's constant, given by this value here. So the energy of the oscillator is quantized, okay? And each discrete energy value corresponds to a different quantum state, represented by the quantum number n. So the oscillator radiates or absorbs energy only when it changes quantum states. So no energy is absorbed or emitted if the oscillator remains in one quantum state. So the oscillators emit or absorb energy in discrete units, okay? And the figure here shows the quantized energy levels and allowed transitions here. So as we said, the main new concept that Planck introduced is the assumption of quantized energy states. And the formula developed by Planck is given by this equation. And the parameter h here was introduced by Planck so that the curve matches the experimental data at all wavelengths, okay? And this parameter value was found to be independent of the material the black body is made of, and also to be independent of the temperature, and it was found to be a fundamental constant of nature. So at long wavelengths, Planck's expression reduces to Rayleigh's expression, okay? And at short wavelengths, it predicts the exponential decrease in the intensity with decreasing wavelength, which agrees with experiment. Okay, so in our everyday life, we do not feel quantum effects because the energy change in a macroscopic system due to the transition between two adjacent states is such a small fraction of the total energy of the system that our senses perceive it as a continuous change, okay? So even though the changes in the energy of a macroscopic system is quantized, we perceive it as continuous, okay? So quantum effects are noticeable at the submicroscopic level of atoms and molecules. Also, when the quantum number n becomes large, quantum physics approaches classical results, and this is known as the correspondence principle. So we will now discuss the photoelectric effect. So experiments show that light incident on certain metal surfaces result in electrons being emitted from the surface. And this phenomena was discovered by Hertz and is known as the photoelectric effect, and the emitted electrons are known as photoelectrons, okay? So the figure here shows a schematic diagram of a photoelectric effect apparatus. And it shows an evacuated tube that contains a metal plate E that is connected to the negative terminal of the battery, and another metal plate C connected to the positive terminal of the battery, okay? And when light of an appropriate wavelength here shines on the plate E, a current is detected by the emitter. And this shows that there is a flow of charge across the gap between the plates E and C. This current arises from electrons emitted from the negative plate E, which is known as the emitter, and collected by the positive plate C, known as the collector. And the figure here shows a plot of the photoelectric current versus the potential difference delta V between the plates E and C for two different light intensities. So as you can see, for large positive delta V values, here the current reaches a maximum value. Also, the current increases as the incident light intensity increases. And if delta V is negative, which means if the battery polarity is reversed such that E becomes positive and C negative, then the current drops, okay? And this is because many of the photoelectrons that are emitted from E, in this case, are repelled by the negative plate C. So only those electrons that have a kinetic energy greater than E absolute value of delta V, where E is the magnitude of the charge of the electron. So only those electrons with a kinetic energy greater than this value will be able to reach the plate C. So if delta V is equal to delta Vs, which is known as the stopping potential, then no electrons reach C and the current is zero. So consider the system of the electric field between the plates and an electron ejected from plate E with a maximum kinetic energy to be an isolated system. And suppose this electron stops when it reaches plate C. So we have from the conservation of energy this equation, and the initial here, it refers to the instant when the electron leaves the metal with a maximum kinetic energy K max, and the final here is the instant the electron stops just before it touches plate C. So let's take the initial electric potential of the system to be zero. Then the final electric potential U final is equal to minus E times minus delta Vs. So from this equation we get K max equal to E delta Vs. So this equation here enables us to measure K max experimentally by measuring the voltage when the current drops to zero, which is the stopping voltage delta Vs. So the experiment shows that the photoelectron maximum kinetic energy is independent of the light intensity, as you can see here, because both curves falls to zero at the same negative voltage, right? Um, so the stopping potential is the same for the metal, even if the intensity of light is different. And this does not agree with the classical approach because, according to this approach, in which light is considered as a wave, electrons should absorb energy continuously from the electromagnetic wave, and when the light intensity is increased, energy should be transferred to the metal at a higher rate, and the electrons should be ejected with a higher kinetic energy. Also, the experiment shows that electrons are emitted from the surface of the metal almost instantaneously, about less than 10 to the minus 9 seconds after the surface is illuminated. And this happens even at very low light intensities. But the classical model shows that at low light intensities, a measurable time interval should pass between the instant the surface is illuminated and the time an electron is ejected from the metal. So, because according to this classical approach, this time interval is required for the electron to absorb the incident radiation before it acquires enough energy to escape from the metal. Additionally, the experiment shows that no electrons are emitted if the frequency of the incident light falls below some cutoff frequency Fc, regardless of the light intensity. And this cutoff frequency has a value that is characteristic of the material being illuminated, okay? And this also is in contradiction to the classical model because, according to this model, electrons should be ejected from the metal at any incident light frequency as long as the intensity of light is high enough, because energy is transferred to the metal regardless of what the incident light frequency is, right? And finally, the experiment also shows that the maximum kinetic energy of the photoelectrons increase with increasing light frequency. And this also contradicts the classical model, which shows that there should be no relationship between the electron kinetic energy and the light frequency, because it shows that the kinetic energy should be related to the intensity of light instead. Then Einstein gave a successful explanation in 1905, where he extended Planck's concept of quantization to also include electromagnetic waves. And he proposed that light or any other electromagnetic wave of frequency f can be considered as a stream of quanta known as photons. And each photon has an energy E equal to hf and moves in vacuum with a speed of light equal to 3 times 10 to the power 8 meter per second. So in this model, a photon of the incident light gives all of its energy, hf, to a single electron in the metal. And so the absorption of energy by the electron is not a continuous process as in the case of the classical model, but it is a one photon, one electron interaction. So let's consider the system as the electron plus the remainder of the metal. So using conservation of energy, we have this equation here, and the energy transfer into the system is that of the photon. Delta E external is equal to hf. And during this process, the kinetic energy of the electron increases from 0 to its final value, which we take as the maximum possible kinetic energy, K max, okay? So the potential energy of the electron plus metal system increases because the electron is pulled away from the metal to which it is attracted, right? So let's take the potential energy of the system when the electron is outside the metal to be 0. So when the electron is in the metal, the potential energy of the system, U, is equal to minus phi, where phi is the work function of the metal, okay? So the work function phi represents the minimum energy with which an electron is bound in the metal. And here are some values of the work function for different metals. For example, for sodium, it is 2.46 electron volt, and for silver, it is 4.73 electron volt, okay? So the increase in the potential energy of the system when the electron is removed from the metal is phi. And if we substitute in this equation, we get this equation here. And in the case the electron makes collisions with other electrons or with metal ions as it is ejected, then some of the energy is transferred to the metal, and the electron is ejected with a kinetic energy less than K max, okay? So going back to the 4 experimental observations that did not agree with the classical model. So first, this equation here shows that Kmax is independent of the light intensity as the experiment showed, and this is contrary to the classical model, okay? And the maximum kinetic energy depends only on the light frequency, as you can see, right? On F, and also on the work function phi. So if the light intensity is doubled, the number of photons arriving per unit time will be doubled, and this doubles the rate at which photoelectrons are emitted, but the maximum kinetic energy Kmax of any one photoelectron will be unchanged. Also, this photon model is in agreement with the near instantaneous emission of the electrons because the incident energy of the light appears in small packets or quanta, and the interaction is a one-to-one interaction between photons and electrons, okay? So even if the incident light's intensity is very low, there will be very few photons arriving per unit time interval, but each photon can have a sufficient energy to eject an electron instantaneously. And also, this photon model explains why the photoelectric effect cannot be observed below a certain cutoff frequency, and it's because the incoming photon must have an energy greater than the work function phi to be able to eject an electron. So if the energy of the incoming photon does not satisfy this, then an electron cannot be ejected from the surface of the metal, even if many electrons per unit time are arriving at the metal in a very intense light beam. Still, the energy of each photon is not sufficient to eject the electron, okay? And finally, if the incoming photon has a higher frequency, then it carries more energy, and therefore it ejects a photoelectron with more kinetic energy than an incoming photon with a lower frequency, okay? So the equation shows that the relationship between the maximum kinetic energy of the electron and the light frequency f is linear, as you can see here, and it was confirmed by experiment, and the slope of the curve, as you can see here, is Planck's constant. And also, from this you can see that the absolute value of the intercept on the vertical axis is the work function phi, which varies from one metal to the other, right? And the intercept on the horizontal axis is the cutoff frequency Fc, and it's given by Fc is equal to phi over h, okay? So the corresponding wavelength, which is known as the cutoff wavelength, is equal to c over fc and is equal to hc over phi. And c is the speed of light. So if the wavelength of the incident light is greater than lambda c, it will not result in the emission of photoelectrons. So we will now discuss the Compton effect. So in 1919, Einstein proposed that a photon of energy E also carries a momentum equal to E over C. So it's equal to hf over C. And then in 1923, Compton applied Einstein's idea of the photon momentum to the Compton effect, which is the scattering of X-rays from electrons, okay? So the classical theory could not explain Compton effect because according to this theory, X-rays are considered as electromagnetic waves of frequency f0. And then according to this, two effects should be observed in the scattering of the X-rays from electrons. The first effect is that the electron should accelerate in the direction of propagation of the X-ray, through the radiation pressure. And we discussed the radiation pressure in the light video 1. So the second effect is that the oscillating electric field should cause the electron to oscillate at the frequency of the radiation detected by the moving electron, which differs from the original frequency due to Doppler effect, right? Because the electron absorbs the radiation as a moving particle, and then it re-radiates as a moving particle, causing another Doppler shift in the frequency of the emitted radiation. And because different electrons move at different speeds, the scattered wave frequency at a given angle should show a distribution of Doppler shifted values according to the classical model, okay? But Compton experiment showed that at a given angle, only one frequency of radiation was observed that is different than that of the incident radiation. So Compton realized that the scattering of the X-ray photons from electrons could be explained by treating the photons as photons of energy hf and momentum hf over c, and by assuming that the energy and momentum of the isolated system of the photon and electron are conserved and they undergo a two-dimensional collision, okay? So in this quantum model, the electron is scattered through an angle of phi, right? As if it is like a billiard ball collision, okay? So the figure here shows the scattering, and the figure here shows a schematic diagram of the apparatus used by Compton, and it shows an X-ray source, and the X-rays are scattered by a carbon target, okay? And after that, it is diffracted by a rotating crystal spectrometer, okay? And the intensity is measured using an ionization chamber that generates a current proportional to the intensity. So the incident beam consists of a monochromatic X-ray of wavelength 0.071 nanometers, and the experimental plots of the intensity versus wavelength for 4 scattering angles theta are shown here, okay? So the plots for the 3 non-zero angles show 2 peaks. One is at lambda naught, and the other is at a shifted wavelength of lambda dash, which is greater than lambda naught, okay? And this shifted wavelength is due to the scattering of the X-rays from the free electrons and is found by the Compton shift equation here. Me here is the mass of the electron, and h over mec is known as the Compton wavelength, lambda c, okay? And it's given by this value. So Compton's measurements were in excellent agreement with this equation, okay? So now let's derive Compton shift equation. So first, as we said, the photon behaves like a particle and collides elastically with a free electron that is initially at rest, as in this figure, okay? So the photon is treated like a particle of energy equal to hf or hc over lambda, and has a mass 0. And in the scattering process, the total energy and the total momentum of the system must be conserved, okay? So if we apply the law of conservation of energy, we get this equation here. So hc over lambda naught is the energy of the incident photon. So Ke here is the kinetic energy of the recoiling electron, and because the electron may recoil at speeds comparable to the speed of light, we use the relativistic expression Ke equal to gamma mec square minus mec square. So we substitute here and we get this equation. So gamma is equal to 1 over square root of 1 minus v square over c square, and v is the speed of the electron. So next we apply the law of conservation of momentum, where we have a two-dimensional collision and the total momentum is conserved in both the x and y directions. So the relativistic expression for the momentum of the recoiling electron is gamma mev, and the momentum of the photon has a magnitude equal to E over c, which is h over lambda, okay? So we get these two expressions for x and y. So if we eliminate v and phi from equation 1 and 3, then we solve and we get an expression of lambda dash, lambda naught, and theta, which is the Compton shift equation, okay? So we will now discuss atomic spectra. So in the previous sections, we discussed black body radiation, and we have seen how all substances at a given temperature emit thermal radiation that is a continuous distribution of wavelengths, okay? And in contrast to this is the discrete line spectrum emitted by a low-pressure gaseous element that is subject to an electric discharge. So this discharge occurs when the applied voltage exceeds the breakdown voltage of the gas. And when this light that is emitted is examined with a spectroscope, it was found to consist of few bright lines of pure color on a dark background, as you can see here. So the wavelengths present in a given line spectrum are characteristic of the element emitting the light. So these wavelengths are like the blueprint of that element, okay? And the simplest line spectrum is that of hydrogen here. And also this figure shows the line spectrum of mercury. And because no two elements emit the same line spectrum, this phenomena represents a sensitive and a practical way to identify the elements present in an unknown sample, okay? And another form of spectroscopy is the absorption spectroscopy, and it is obtained by passing light from a source emitting a continuous spectrum through a gas or a dilute solution of the element that we want to analyze. So the absorption spectrum consists of a series of dark lines on a continuous spectrum background, okay? And this is the absorption spectrum of hydrogen. And in general, some of the emission lines may not be present in an absorption spectrum, okay? And one of the applications of an absorption spectrum is in identifying the elements in the solar atmosphere. And this is because the sun emits a continuous spectrum of radiation, and then this radiation passes through the gases of the solar atmosphere and also through the Earth's atmosphere, okay? And between 1860 and 1885, many scientists collected a lot of data using spectroscopic measurements, and in 1885, the Swiss scientist Balmer found a formula that predicts the wavelengths of 4 of the emission lines of hydrogen. And these lines are H alpha, which is red, at a wavelength of 656.3 nanometer, H beta, which is green, at a wavelength of 486.1 nanometer, H gamma, blue, at 434.1 nanometer, and H delta, which is violet, at a wavelength of 410.2 nanometer, okay? And the emission spectrum is also showing other lines here, okay? So the wavelengths of these lines, which is known as Balmer series, can be found from this equation. And n starts from 3 and 4, etc. And RH is known as Rydberg constant. And if the wavelength here is measured in meters, then the constant is given by this value, okay? So the first line in the Balmer series of a wavelength of 656.3 nanometer here corresponds to n equal 3, and the second line is n equal 4, and so on. So following Balmer's discovery, other line spectra for hydrogen were found, and they are Lyman, Paschen, and Brackett series, named after their discoverers, okay? And the wavelengths of the lines in these series can be found from these equations. So next we will discuss Bohr's quantum model of the atom. So again, classical physics failed to explain the atomic spectra, and that was in the beginning of the 20th century. So it was not clear why atoms of a certain element emit only specific spectral lines, and also why the atoms absorb only those wavelengths they emitted. So in 1913, Niels Bohr provided an explanation that included Planck's quantum theory, Einstein's photon theory, and also Rutherford's model of the atom. So Bohr constructed a model of the hydrogen atom, which is the simplest kind of atom, and it contained some classical features as well as new ideas, okay? So first, the first point is that the electron is considered to move in a circular orbit around the proton under the influence of the attractive Coulomb force, right, between the electron and the proton. So the Coulomb force here is the centripetal force. And second, that only certain orbits are stable, and they are the ones in which the electron does not emit energy in the form of radiation. And the total energy of the atom remains constant, and classical mechanics can be used to describe the motion of the electron. And the third point in Bohr's model is that radiation is emitted by the atom when an electron jumps from an orbit of a higher energy to a lower orbit, okay? But this jump cannot be visualized or treated in a classical way. And the frequency of the emitted photon when the electron jump is related to the change in the atom's energy. And it is given by, the frequency is given by this equation. So if E initial minus E final is equal to HF, and E initial is greater than E final, okay? So the frequency of the emitted photon is not equal to the frequency of the electron's orbital motion, as was thought by classical physics. So E initial is the energy of the initial state, and E final is the energy of the final state. And also the fourth point in Bohr's model is that the size or radius of the electron orbit is determined by a condition imposed on the electron's angular momentum here. So the allowed orbits are those for which the angular momentum of the electron in its orbit about the nucleus is an integral number of h bar, okay? And h bar is equal to Planck constant h over 2 pi, okay? So we have this equation for the quantization of the angular momentum. Also, we have the electrical potential energy of the system is given by this equation, okay? Because so Ke is Coulomb's constant, and this is from the attractive force between the electron and the proton. And so the total energy of the atom is given by this equation, which is the kinetic plus the potential energy. And we have from Newton's second law, which is force equal mass times acceleration, this equation where v square over r is the centripetal acceleration, okay? So mv square over 2, which is the kinetic energy, we can find it from here to be equal ke e square over 2r. And if we substitute this here into this equation, we get an expression for the total energy of the atom, which is minus Ke E square over 2r, okay? And note here that this total energy is negative. And this indicates that the system is a bound electron-proton system, okay? So an energy of plus Ke E square over 2r must be added to the atom to just free or to just remove the electron and make the total energy zero. And from the quantization of angular momentum, you can see v square here is equal to n square h bar square over m square r square. And v square from here is also equal to ke square over mr, okay? So we equate them and we get an expression for the radius of the allowed orbits in the hydrogen atom, okay? For n equal 1, 2, etc. And so as you can see, the radii have discrete values, so they are quantized. So only certain orbits are allowed, okay? And the orbit with the smallest radius, known as Bohr radius, A0, corresponds to n equal 1 and has the value of 0.0529 nanometers, okay? So we may write Rn in terms of the Bohr's radius, so Rn is equal to n square A0. So the first three Bohr orbits are R1 equal to A0, R2 is equal to 4A0, and R3 is equal to 9A0, okay? And so on. So this quantization of the orbit radii leads to energy quantization, because if we substitute Rn into this expression here, we get the quantized energy levels. And if we substitute for the values of these constants, we get this expression, which is minus 13.6 over n square electron volt. So the lowest allowed energy level, also known as the ground state, corresponds to n equal 1 and is equal to minus 13.6 electron volt. And the first excited state, or the next energy level, corresponds to n equal 2 and is equal to A1 over 4 equal to minus 3.4 electron volt here. Okay, so this is the ground state and this is the first excited state. So this figure here shows an energy level diagram showing the discrete energy states for each quantum number, okay? And the uppermost level is when n is equal to infinity, which gives r equal infinity and e equal to 0, right? And it represents the state for which the electron is removed from the atom. And the minimum energy required to ionize the atom, which means to completely remove an electron in the ground state from the influence of the proton, is known as the ionization energy. And based on this, the ionization energy for hydrogen is 13.6 electron volt. And this prediction of Bohr's theory for the ionization energy was in excellent agreement with the experimental results, okay? So using the third point that we discussed in Bohr's model, the frequency of the photon emitted when an electron jumps from an outer orbit to an inner orbit can be calculated from this equation here. And since c is equal to f times lambda, we have this equation for the wavelength. And this formula, which was derived by Bohr based on first principles, is identical to the form of empirical relations discovered by Balmers and others that we mentioned earlier, this formula here. So the theoretical constant derived by Bohr, this one here, is equal to the experimentally determined Rydberg constant RH to a precision of about 1%, okay? So Bohr showed that the spectral series of Balmer and others for hydrogen are transitions between energy levels in the hydrogen atom, okay? As you can see here. And then Bohr extended his model for hydrogen to include other elements where all but one electron had been removed, such as, for example, the ionized element helium+. So for a single electron orbiting a fixed nucleus of a charge plus Z, E, so imagine you have a single electron orbiting a nucleus that contains Z protons. So Z is the atomic number of the element and it represents the number of protons in the nucleus, right? Then the radius of the orbit of the nth level is given by this equation. And the quantized energy levels, the allowed levels for that electron is given by this equation. So we will now discuss Bohr's correspondence principle. So this principle states that quantum mechanics is in agreement with classical physics when the difference between quantized levels vanish, okay? because as you can see here, for large values of n, the energy differences between adjacent levels approaches zero. And so the levels are nearly continuous here, okay? And therefore, the classical model can be accurate to describe a system with large values of n. And according to this classical model, the frequency of the light emitted by the atom is equal to the frequency of revolution of the electron in its orbit about the nucleus, okay? And for n greater than 10,000, this frequency, predicted frequency of classical physics differs from that predicted by quantum theory by less than 0.015%. So we will now solve an example. So suppose a 1 kilogram block is attached to a massless spring of force constant of 20 newtons per meter, and if the amplitude of oscillation is 0.4 meters, find the total energy of the system and the frequency of oscillation according to classical mechanics. And then, assuming the energy of oscillation is quantized, find the quantum number n of the system, okay? So the total energy of the block spring system is equal to half Ka square, equal to 1.6 joules, and the frequency of oscillation is given by this equation and is equal to 0.7 hertz. Okay. So if the energy of the oscillator is quantized, the quantum number n of the system is equal to En over hf, and this gives n equal to 3.45 times 10 to the 33. So as you can see, n is very large, which is typical for macroscopic systems, okay? So suppose the oscillator makes a transition from this state here to another state that differs by 1, okay? And we want to find the change in the energy of the oscillator for this one quantum change, okay? So the energy carried away due to a transition between two states differing in n by 1 is equal to hf, right, from the previous slide. So if we substitute for h and f, we get this energy here, okay? And this energy is only this fraction of the total energy. So it's about the order of 1 part in 34, okay, in 1 part in 10 to the plus 34 joules. So it is such an extremely small fraction of the total energy of the oscillator that it cannot be detected, okay? So even though the energy of a macroscopic system is quantized and thus change by small quantum jumps, our senses perceive it as a continuous change, okay? And this is why quantum effects are detectable and important only at the submicroscopic level of atoms and molecules. So in the following, I included some more solved examples. So thank you for watching. Please don't forget to like and subscribe, and see you in the next video.